journal, even though it's really good.
Kasabov also did this.
Yeah, Span. I mean,
he did everything, I think.
Oh, you know Kasabov?
Of course.
Yes, okay. Oh, you are from Bulgaria as well?
Sorry?
You are from Bulgaria as well?
No, I'm from Russia, but I met him on conferences.
Yeah, that's where you meet him.
But he has probably papers on neural network in every area.
Yeah, he's got his fingers everywhere. I mean, you can't
not at all this.
Yeah, I mean, actually, it mainly was driven forward by Stefan Schliebs, who was a lecturer in his group at the time, and Mohammed Mohammed, PhD student at the time, so it was Span. And then there's lots of work which is more, I mean, this is all inspired more from, top-down view, computer science view, machine learning view. And then there's lots of work from the Gerstner group, SEM group, also around this, who are coming more from the neuroscience. So they want to do learning, and they want to do something that's really biologically realistic. So lots of challenges on the way. Probably we are not going through. I mean, I've already mentioned the discontinuous nature of spikes. When most error functions consider real value in time continuous quantities, so you have to think about how to linearize or how to kind of smooth out the discontinuities. There are different ways to do this. Smear out spikes. I mean, obviously you're reversing the delta function by smearing out with some continuous kernel to make it into something smooth again. So we are back at some smooth influences. And the most interesting thing is you treat neurons as stochastic. We'll come to that on a later slide, perhaps a bit again. Whereby you see that spiking is not a deterministic process, but that you don't have a fixed threshold when you fire, but that the probability that you fire increases with the potential you've got. And this namely allows you to assign a neuron an underlying smooth probability of firing, so an instantaneous firing rate, as an intensity of a point process in mathematical terms. It's a stochastic process. And this is smooth again, and with that you can do derivatives and all this stuff again. So there are ways of computation is obviously closely related to encoding and decoding with spikes. So how do you encode information to spikes, decode it from spikes again? I think this also was mentioned a bit. There's the inherent notion of time implied by temporal extension of spike trains. So a rate neuron is always in almost discrete time steps, but because the spike train extends in time, even with a network that is not recurrent, you have to consider temporal effects. Relating models of computation with biological spike neurons, also challenged to make this in a biologically plausible way. Reconcile it with different neural models and so on. And so there are many interesting things. Mathematical formulation is very difficult due to the explicit extension in time. So all the quantities that you have are indexed with a lot of indices, n with time and so on. So it seems the format of this is different from what I see on the screen. So there's another line there that doesn't get it. Good. Good. So, our approach, I've mentioned before, we want to generalize backpropagation to spiking neural networks, and we don't want to have just a single layer or a two-layer network, we want to have an in-layer, so a more complex network.
Sorry, that would be revolutionary. I mean, if you manage to do backprop with anything that has more than 3 layers, I mean, I guess that would come down to how local minima are being handled and the optimization.
Yeah, I mean, you're now, in principle, you can use backpropagation for as many layers as you like, but the error signals are decaying exponentially.
Yes,
so this, you will have the same problem. You will have the same problem.
Yeah.
So there's this famous paper by Benjo, that's probably what you are related to. So we're not overcoming that. So, I mean, yes, backpropagation is fine, it's general, but it's also got its drawbacks, and there are kind of thousands of ways to overcome them or not. People will be stuck exactly with the same problems, but not for rate neurons, but for spike neurons. But nobody really knows it now for spike neurons because nobody has really tested it, we have just developed it. So. Okay, and we want to use a stochastic neural model to connect the smooth quantities where derivatives exist with the discrete spike trains where no derivatives exist. How to say what a derivative is. Okay. We want derivatives because backpropagation is inherently derived by using, well, derivatives of the error function.
So no derivative doesn't mean it's discontinuous. So exactly what I was talking about.
No, if something is discontinuous, if something is not smooth, then you have a hard time to find a derivative.
But you have functions which are continuous everywhere but differentiable nowhere.
Yeah, let's not get into mathematical discussions. I mean, you mean the famous sign of 1 over x or something like that. Or x times cosine 1 over x. Yes, no, fine. I didn't mean to go into this detail. I'm not showing you the derivation, but in the course of the derivation, you're also swapping quite freely derivation and integration. And obviously, well, if you want to do it waterproof, then you have to do it mathematically correct. But I'm not going into that much detail. Good. Do you want to know methods or not?
Yeah.
Give it to us. Boring. So, that's the neural model we've got. Okay. U is the membrane potential. W is obviously the synaptic weight between output neuron or some postsynaptic neuron O and presynaptic neuron H. We've got a spike train that comes in here, and the spike train is just a sum of delta functions. Okay, so where TH is the firing time in this spike train, or firing times in the spike train. I mean, obviously we're only taking the firing times up to time t, so we wanted something causal, so TH must be smaller than the time t we're looking at. This is the spike train that comes in. It's convolved with the spike response kernel, so we get something smooth. We see this on a figure a little bit later. That gives you kind of a contribution to the potential, and you kind of weigh it with the weight of the synapse. And this is just another term. This is the spike train of the output neuron itself, of the neuron O we're looking at. Because each time we fire a spike, there was this kind of, the voltage, potential went down and had to go up to the resting pushing. So this is the refractory kernel.
It's basically a bias term, in effect.
Okay, so this is a membrane potential. This is entirely deterministic. We have spikes coming in here and here, and you calculate kind of a real number quantity, which is the membrane potential at a time. Good.
So you're counting number of spikes,
We are not really counting them. I mean, they're implicitly counted in a leaky. It's leaky integrated file. I mean, essentially, the kernels are always modeled like this: that the neuron functions like a leaky integrated file. So spikes coming in at a certain time. Then the effect on the membrane potential decays according to the kernel E.
So this is epsilon is a
Epsilon, sorry. That's the kernel we come to it on.
That's a pretty good question.
Epsilon usually looks like something like exponential increase or, well, linear increase and exponential decay. That's what it looks like. And this is epsilon, and K usually looks like something negative. It's something that when a spike appears, you are kind of quite negative, and then goes up positive and decays exponentially.
And the standard deviation is typically much larger than the interspike distance.
I wouldn't say that.
Really, always. So this can still be very discrete even after the convolution.
Yes, you'll see how it is. I mean, the decay constants of these are in the order of milliseconds to tens of milliseconds, which is also often the same order of magnitude as the interspike interval. So you really, I mean, for this kernel, you really have to have 3 spikes or whatever it is coming in very close to each other. Okay, so spike response kernel epsilon is this one, and the reset kernel, as I call it here, is this one. And we should have, yes, it's 5 milliseconds for the 10 milliseconds. So this is a superposition of 2 exponentials. So one is the rise time, and it's this 5 milliseconds, the other was UK 10, which is 10 milliseconds. It's quite typical, you can measure these, actually. Yeah, some scaling constants, 5 blah, blah, blah. Step function brings us the function because you only want the parts of these kernels for positive times, because that's the causal part. Right? Just like one filter. Okay, that's an ingredient. Stochastic intensity. So this is how to convert the membrane potential U, which we've seen on the 2 slides before, convert it back into a spike train. So how do you do this? We don't have a clear cutoff here. We are just saying that the stochastic intensity of the process depends on the potential like this. So you can see that some of the smoothness which this increases with increasing potential depends on delta U, which is, if you like, something like the variance with which the spiking would happen at a certain point. So large U values mean we have a lot of smoothness, so the probability of firing changes at the threshold just a little bit. If this gets close to 0, then it changes quite a lot. If you make this 0, then you have a deterministic rule that fires when this is above, when U is above theta, it doesn't fire at all. It's below theta. So rho is the stochastic intensity. How do you convert the stochastic intensity then to a probability of firing or not? So you know this is you just need to integrate over time. So rho is something like gives you rho multiplied with a small time interval gives you the probability with which a neuron fires at this moment. Right? Just the same as between probability densities and probabilities. So it's essentially probability density. So this is smooth quantity. It exists at each time and it governs whether you spike or not. So our neural network has a stochastic component in there. And it's just used here. We introduced this not for any intrinsic, not for the. Our goal is just here to have something that where a smooth quantity describes a discrete process, the spiking, because we want a smooth quantity. It's not here to model noisy neurons as such. I mean, they are noisy, but this is not our intention.
But U of t can be unbounded potentially.
Yeah, it isn't in practice. Because look, if this is 1 and this is 10 and this is 9 and this is 1, say, then we have, I mean, e to the power of 9, which is quite large. So the intensity of this will be quite large. So the probability in 1 millisecond to fire will be more than 1. So you will likely get 1 or 2 spikes in it.
Okay, so it approaches, yeah, it's kind of almost like delta function in terms of probability density. Yeah? So when it becomes infinite around something.
If this becomes 0, then this obviously becomes something that behaves like a distribution. But I mean, it's just something when theta. Let me not draw this now and fail. I'd rather do it after the talk. Good. So how many more minutes do I have? 10? Or
As many as you want.
Well,
We have 2-hour slots.
Oh, it's a 2-hour slot.
Yeah.
Oh.
We usually take it for an hour. Then we rarely run over. So,
That's so nice of you.
take as much time as you want. You got 59 minutes.
Okay, my intention is not to use them anymore. But, good. Good. So next thing is obviously we have to say, so this is the neuron. Right, and this is for the neuron how it connects to others. Details of it, how to convert the membrane potential into law, stochastic intensity. Yeah, we also have to talk about error functions. What is the error? I mean, for rate neurons, you have a real number value, and your target is also a vector of real numbers. And then what you do is the error function is you take the Euclidean distance, or you take I don't know, some log likelihood, or cosine distances. I mean, there are many forms of distances that you can take between a real number vector, that is your output of the network, and a real number vector, which is the target of the network. Here you have to work a bit differently. There are also several choices, but when you look at them, it doesn't really matter. Just like for rate neurons, it doesn't really matter whether it's the cosine distance or it's the Euclidean distance, because in the end they behave quite similar. What is quite amazing is that given this stochastic intensity, and given target spike train, reference spike train, I mean, this is the spike train that you want your network to learn, you can calculate what the probability is of you getting the spike train. Okay. This result is quite amazing, but the calculation is in fact quite simple. I mean, you think, oh, how can this be? It's
Probability of what?
this is the probability given a certain input for a single layer network. Or, I mean, we're talking about a single neuron in principle. Given a number of input spike trains, you can calculate raw, because raw only depends on the input spike trains. And given raw, you can calculate what is the probability that a certain spike train, a given spike train, is produced. Or rather, I should say probability density, because there are obviously many different spike trains.
But of course, that's because if spike is a continuous function, then yeah, it's you cannot describe it as it must be a discrete test. Okay.
No, it's I should be more precise and say this is probability density. This probability density of getting a spike train which is firing like this time, this time, this time, this time, this time. Yeah. You can calculate this. But
okay, that's what it. Because it looks like Z capital, and then there's like Z small. And I can't see them different.
Yes.
No. Are they the same? The one on the integral?
You're absolutely right, and I think you're a mathematician originally. Otherwise, I wouldn't get these questions. And indeed, this is a capital Z, and this is a small z. Because the PhD student like to distinguish between the spike train abstractly and the spike train kind of written. I've told him to stop that and abuse the notation, but obviously when I did the slides, when I prepared the slide, I overlooked it. So it should be small z or capital Z. It should mean the same. Yeah, so I should clarify. So that's the same. So anyhow, you've got this handy expression to get the likelihood or probability density of producing a given spike train given input. So the error function is now quite clear. What you want is, given the input to the network, you want to maximize the probability of producing the spike train. So that's the error function. So you're not doing gradient descent here, you're doing gradient ascent. Doesn't really matter. You can also use other distance functions between actual outputs and target outputs. For example, the Van Rossum distance, some of you might know. Doesn't really matter. So we've got now our network, we know how the single neurons function, we know how to plug them together, we know what the objective error function is, and then we just kind of let the backpropagation approach roll. And the backpropagation approach is quite simple. You just take the error function, in this case you take the logarithm probability, because it has mathematically nicer properties, because you get rid of the exponential here. And you calculate the derivative of this with respect to a parameter of the network rate, and you use this, we're doing Sm, so a low minus sign here, is your change of rate. So this is the simplest approach. This is how backpropagation is done. So where all the work lies is kind of calculating these in a nice way. Right? So this is the ansatz, but calculating this is quite a nightmare.
It's a kind of like gradient descent.
Yeah, sure, it is. But I mean, that's trivial. I mean, it's trivial to write this down, but calculate these in an interesting way, in a nice way. That's the thing. Okay. Good. So, and that's the pain, as I've said, and I could show you some 10 slides of doing the calculations. With lots of derivatives, indices, probabilities, probability densities, logarithms of probabilities, condition probabilities, Derivatives are only possible due, so functional different derivatives, sometimes not normal different, just because objects are extended in time. And freely switching between expected values, means, which are smooth, and the best estimates, right? For probabilities, we sometimes need properties of the underlying distributions, like means and so on. How do you estimate a mean if you can't sample it a million times? You take the best shot. The best shot is the only sample you've got, so like say, the best estimate you get. And things like that. Then what comes out is this. Okay. You define a backpropagated error signal, which looks pretty similar to what you do for normal backpropagation. And for the hidden to output weights for one layer neurons, you get this expression for weight change. Okay. This was done by Pfister and Coerce, so Gerstner group. Okay, we took this and we drove it one step further for the input to hidden weights. I mean, this is also our creation. I mean, they didn't have any multi-layer in mind, so. But we tried to impose this backpropagation scheme so that we could iterate for more layers. And what comes out then? In a lengthy calculation, gets much more complicated because you have two convolutions with kernel epsilon, one for one layer, one for the other layer. You take products of these. What is a product of delta function? We don't know. But if you integrate out on the delta functions away, so you can give a meaning to this, especially because you're breaking it down in time steps anyway. And you get this update. So, we've got this now, so we can train hidden neural networks with spike neurons with hidden weights, with hidden root neurons. The question is, as always, when you've derived it theoretically, will it work in practice? And that's what we're doing now. So, purpose was to explore the properties of the neural learning network. Is it working at all? Okay. So the task which we are using here is a combination of mapping and classification task. So we give an input to the network, which is given as a set of spike trains. And for each different set of spike trains, we say produce us an output, which again is a spike train. So it's a mapping task. You give an input spike train, and you want the network to learn to respond to it with a certain output spike train. Okay. For some reason, Brian liked classifiers. He was a PhD student, and I couldn't prevent him from doing this. So what he does is he even has several different input spike trains that should map to the same output spike train. So we're doing both mapping and classification in the same task. Makes it a bit more complicated to understand. But we're mapping input spike trains to output spike trains. We're learning that, and we're also classifying in the sense that different input sets of input spike trains shall be mapped to the same output spike train. Good. So what does it look like? Error measures. The Van Rossum distance is a distance where you measure how different two spike trains are. We use this for the performance plots.
So, what is that distance roughly based on?
The Van Rossum distance?
Yes.
It's quite simple. When you have two spike trains, okay, and these are delta peaks, and you kind of take the difference of them. You have a delta here, delta here, delta here, delta here, delta here. So if they're not exactly at the same time, you get a massive contribution to the error. We don't want this. So what you do is you smear out each spike with some exponentially decaying function. Right.
So this is unrelated to the...
And then you take the product of these spike trains. Not just the standard Euclidean integral product. And this, I mean, there are other means to do it, but this is the easiest. So this measure accounts at the same time for deviations and also for missing sprays. There are some parameters where you can give different weights to different aspects, but it doesn't really matter. Okay. So, and a trial is classed as a success if the Van Rossum distance of the produced output spike train agrees more with a target spike train than with other output spike trains that would be the outputs to other input patterns. Simulation details, we have got 100 input neurons, simulation time step is 1 millisecond, lots more parameters which I don't report here, which might or might not be significant. We don't know yet. Okay, so once more a network, so we have input layer, output layer. What does an input to the network look like? It looks like this. This is the time axis here, and these are the 100 input neurons, and each line of this is kind of the spike train that is input through through neuron 0, 1, 2, and so on, 20, 30, 100. So input patterns look like this. Okay. So there are different such input patterns, and each one shall have a different output. So for this pattern, the output happens to be regular starting. It doesn't have to be regular, it just happens to be the prime starting with letting the spike at 80 milliseconds, 160 milliseconds, but you can also take other numbers. And so what you see here is, again, time. And you see a number of training episodes. And you can see that these are the target spike times. And what you can see is that initially there is some deviation around target spike times. But then spiking of these neurons quite fairly converges to the output spiking that you want. Okay, this is the activity in the hidden layer. Again, it's the spike raster, so time is this axis, and episodes are here. So you can see that in the hidden layer you have a lot of activity going on here and here and here. But as you train, it's dying out.
How many hidden neurons do you have?
In this case, I don't know.
Is it like 10 or?
Yeah.
And you have one output.
A small natural number. I mean, we had maximally up to 30 or 40, 50. And in this case, it's just a single output we have, but we have other experiments with up to 30 different outputs, where each output produces a different spectrum. What you can see here is the distance, measured as the von Rossum distance. It's the number of episodes. It's going down, so it means this spike output is the output of the network converges to the desired target output quite fast. I mean, this is typical learning curve, as you also see for so in principle it's working. I mean, this was the simplest case. I think this was one of the first experiments Brian did with just a single output, and also just a single input and a single output. So in some sense it's quite trivial, but I think it's first to purpose.
Would it be possible to compare that with a baseline that would be, I guess, an autoencoder, something like that, where basically you'd obviously have to remove the spike train aspect of it, so you'd have to have some sort of conversion from grayscale to spike frequency, but potentially with the same number of neurons, one could train with the same episodes.
Yeah, comparison is always good. We haven't thought along those lines. I mean, what we are doing currently is compare this with other spike network learning algorithms. Okay, what do we see here? Here we see the output layer in principle. And the output layer gets inputs from the hidden layer. And what you see here is the fluctuations of one hidden neuron output membrane potential. So this is the firing threshold, and I will presume everywhere you get these spikes, it has spiked indeed. And so this is fluctuating. This is also quite typical for spiking neurons and looks similar to what you get for real neurons and so on. So spikes are coming in from the input layer, and then the potential goes up, and then after a time it's decaying again. So this is roughly what you get. So what of this is conveyed to the output of the hidden neuron? So what is the input to the output neuron? This is the potential somehow convolved, and not the potential bit, but only taking the spikes convolved with the kernel. So and what you see here is that you get this, and you see that the kernel decays faster than this spike interspike interval. Not here though, but here and here. So it's in the same order of magnitude. Okay, and then this is fed along with other neurons, other hidden neurons into the output, and the output has a similar behavior. It's not as rough as it is, but smoother. Different parameters have been used. You can see that the output neuron fires down here and has some fluctuations around the fire times, and the dotted lines are where the target fire times are. And what you see here is how the weight changes in time. So this is replay to the one hidden neuron has this activity, gives this input to the output neuron. The output neuron fires here and here, and this is kind of the weight changes you see between this hidden and this output neuron. So in this case, this neuron becomes stronger in the course of learning over this 1%. And you see it's going. You have this rebound effect here, and this is simply because the output neuron fires a bit too early, so we have to weaken that weight for a moment. But you see that it's very thin, so we are kind of on target now. This, in principle, is the same, but a different hidden neuron and different input neuron. I mean, we can also see the input. So the input is just a spike train, spikes here, 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 here. This is what the hidden neuron sees of the input spectrum filtered through the spike response kernel. Then this is fed into the hidden neuron, which fluctuates like this, but it's got many connections to many other inputs. So this is not the only driver of this graph here. So there are many other input neurons that drive this as well. And in the term that updates the hidden to output weight, the input to hidden weight, we have this double convolution of the spike train of the input neuron and the hidden neuron. When you do this for this neuron, for this activity of the hidden neuron and this input neuron, what you get then is this. Okay? So this is the driver of the weight changes, and they're kind of depicted here again.
Sorry, so what you're showing on the bottom right is one run of a spike train, and the weight's changing through
it's one episode, so to speak.
Yeah. So I've got a spike train flowing through, and while that's happening, the weight of the synapse is dropping because I don't understand why.
Because the output neuron fires slightly before it should fire.
Why? Because
you are
so there's a spike.
Yes.
I'm just trying to understand the chart. There's a spike where the bars are, the dashed bars are.
Indeed.
Yeah. So the spike.
Yes, you can see that here's the green spike. Well, the green shows that the spike is happening for the output neuron, and you see that it's happening slightly before the target. So let's say
it's only got one spike. So what it does is the weight goes down.
Yes.
There's a spike, and then the weight comes back up.
Yes.
So the weight changes when the neuron is not spiking.
Yes, the weight changes at 2 times. It can change when the output neuron is spiking or when the output neuron is expected to spike but doesn't. So it changes negatively when the output does spike.
Early.
When it's not expected to spike, so this is here, it goes down. Goes down because it spikes too early. So the neurons that made this fire contributed a bit too much. I mean, this is not a single neuron. These are kind of 10 neurons or so that contribute here. But you're just seeing kind of the interaction between one hidden neuron and between one of the 10 neurons of the output neuron. But this is the collective behavior of the output neuron. And the output neuron fires too early, so some of the weights are too big. Because if they were a bit smaller, you would need another spike to make it fire a bit later. So
some of the weights go down.
Exactly.
And then lots of the weights go up, and the aggregate weight goes up.
Yes. But essentially what you see here is